Hello, myself Dr. Anuj Purwar. Today we'll discuss hydraulic consideration and designing part 3. Water hammer. When water is flowing in a pipe, it possesses momentum on account of its motion. If this flowing water is suddenly brought to rest by closing the valve, the velocity of water column behind the retarded and its momentum gets dissipated, which causes a very high pressure on the valve. This high pressure is followed by a series of the pressure vibration. The pressure vibration set up noises in the pipe which is known as the knocking. The sudden rise of pressure in a pipe has the effect of hammering action on walls of the pipe and is known as the water hammer. In water means sometimes the hammer blow is so high that it may even burst the pipe. That is why utmost care is taken to close the valves, especially that of mains gradually. Pressure rise due to the water hammer depends upon the velocity of flow of water in pipe, the length of the pipe, time taken to close the valve, and elastic properties of the material of the pipe. There may be following cases of water hammer: gradual closure of valves, sudden closure of valve, considering pipe to be rigid, then sudden closure of valve, considering pipe to be elastic. Hammer when the valve is closed gracefully. Considering a pipe length L, cross-sectional area A, through which water is flowing with a velocity of V meter per second. The valve is closed gradually to stop the flow of water, and time taken in closing the valve is T second. Let increased pressure due to closure of valve be P, then mass of water in the pipe is equal to gamma AL upon G. Rate of retardation of water is equal to velocity upon time is equal to V upon T. Then force is equal to mass into acceleration is equal to gamma AL upon G into V upon T. So intensity of pressure rise in value is equal to P is equal to force upon area is equal to, then comes gamma LV upon GT. Hence, pressure head due to the increase in pressure is equal to HW is equal to gamma LV upon GT upon gamma is equal to LV upon GT. Water hammer when the valve is closed suddenly. The increase in pressure due to water hammer is equal to gamma LV upon GT. T is time taken in closing the valve. If the valve is closed suddenly, T will be 0, and in that case increase in pressure due to water hammer will be infinite. Since it is not possible to close the valve in 0 time, hence the pressure might not be infinite but may be high depending upon the value of the T. It has been considered that water flowing through pipe is incompressible, but in such cases water gets compressed to some extent. Let K is equal to modulus of elasticity of water or bulk modulus of compression of the water. When the flowing water is suddenly brought to rest, the kinetic energy of water is converted into strain energy stored in the water. So mass of water in the pipe is equal to gamma AL upon G, and kinetic energy of water is equal to mass into velocity square upon 2 is equal to gamma AL upon G into V square upon 2 is equal to gamma AL V square upon 2G. Strain energy stored in water is equal to 1 by 2 P square upon K into A into L. So on equating the equation, we will get P is equal to V into root K rho, where rho is equal to gamma upon G is equal to mass density of the water. Now water hammering case pipe is elastic. It can be proved that increase in pressure in such case P is equal to V into root gamma upon G into in bracket 1 upon K plus D upon ET, where E is the modulus of elasticity of the pipe material and Poisson ratio has been assumed as 1 by 4th for obtaining the value P, or we can say increased pressure. The circumferential stress Fc or longitudinal stress F1 can be obtained by equation of strength of material. Now here the example. A valve at the outlet of a pipe is closed suddenly to bring water to the rest. Find the pressure increase due to sudden closure of valve if water was flowing in the pipe at a velocity of 3.5 meter per second. Bulk modulus of water may be assumed to be 2 into 10 to the power 4 kg per centimeter square. So here velocity is given is equal to V is equal to 3.5 meter per second. Bulk modulus K is equal to 2 into 10 to the power 8 kg per meter square. So pressure increase due to sudden closure of valve is P is equal to V into root K gamma upon G. So value comes up 49.97 kg per centimeter square. Now types of the pipes. Depending on construction materials, following three types of pipes are available for various uses in the water supply system: metal pipes, cement concrete pipes, and plastic pipes. Metal pipes. Following types of metal pipes are used: cast iron pipes, steel pipes, wrought iron pipes, and copper, lead, and brass pipes. Cement concrete pipes. Cement concrete pipes are of following types: pre-stressed concrete pipes, reinforced cement concrete pipes, plain cement concrete pipes, glass fiber reinforced concrete pipe. Plastic pipes. Following types of plastic pipes are used: unplasticized polyvinyl chloride and UPVC pipes, polyethylene pipes, glass reinforced plastic GRP pipes. Joint in water supplying piping. Joints are the most vulnerable points where there are chances of leakage if pipes are not joined properly. The upward end of the pipe is brought to fit into and align with the downward end of the previous pipe, and then joint is made watertight with a joining material. Joining material for the pipe joint. There are some cementing materials such as lead or cement mortar are available. An ideal joining material should be impervious in nature, should be elastic and have sufficient strength and be durable. Easy availability in market and is also an important factor. It should have good adhesive property and workability. Now types of joints. Following are the common joints in joining water mains: spigot and socket joint, flange joint, expansion joint, and collar joint. Spigot and socket joint. The joint is also called bell and spigot joint. The enlarged end is called socket or bell, whereas the normal end is called the spigot. The normal end spigot is fitted into the socket and proper alignment is done. The joint is made by caulking in spun yarn and then filling the remainder of the joint space by molten lead, taking care that no dross enters the joint, and then thoroughly caulking the lead. The molten lead solidified quickly and makes the joint watertight. All this discussion is shown in figure. Here the two pipes. One is the position known as the well in this figure, and another is the spigot. Spigot is enter in the belt or socket, and the portion is filled with the jute and the remaining portion is filled with the lead. Flange joint. Flange joint are generally used at location where it becomes necessary to disjoint the pipes off and on, such as at pumping station, filter plants, etc. Two flanges are put together and a rubber washer known as gasket is kept between flanges and fixed by means of nut and bolt. The gasket is not less than 1.5 mm thick. The joints are strong, rigid, and easy to repair. Here we are seeing the picture flange joint. This here the two pipes are flange pipes are joints are close together, and in between a rubber washer is provided. This is known as a gasket, and it is tied with the nut and bolt. Expansion joint. Expansion joints are provided in metal pipelines at suitable intervals to take into account the change in pipe length due to temperature variation. The socket end is connected rigidly to another ring which slides freely over the spigot end. A small gap is kept between the face of the spigot and inner face of the socket. A rubber gasket is provided between the socket and the spigot. Finally, they are tightened with nut and the bolt. As here we are seeing in the picture, this is an expansion joint. In between, it is rubber gasket is put, and a gap is made between these two positions, and it is tightened by the nut and bolt. Collar joint. The concrete pipes are mostly joined by the collar joint. Pipes are having a spigot at one end and the socket at the other end and joined by a gasket or hemp and clean cement. It is further strengthened by providing a concrete collar wide enough to cover the overlap of the joint. Pipes of bigger diameter are joined with collar joint. Pipes without sockets are put butting together and joined with collar. Here the we are seeing the picture as we had discussed the joint collar joint. Testing of mains. After laying and jointing, the main has to be tested for the leakage. Following procedure is adopted for the testing. The main is slowly discharged with water so that all air is expelled from the main by providing a 25 mm inlet with a stopcock and allowed to stand filled with water for a few days and then tested under pressure. The test pressure is usually 5 kg per centimeter square or maximum working pressure plus 50%, whichever is greater. The pressure is applied by means of a manually operated test pump or in case of the long mains or mains of large diameter by a power driven test pump. The test pump having been stopped, the test pressure will maintain itself without measurable loss for at least half an hour. The main is tested in section as the work of laying proceeds. It is preferable to keep the joints exposed for inspection during the testing. The open end of the main is temporarily closed for testing under moderate pressure by fitting a watertight expanding plug which is available in the market. The end of the main and the plug is secured by struts to resist the end thrust of water pressure in the main. Air should not be used for testing water main. The test should be done always with water. For more details, we can refer the IS code 2065 1972. This is all about the hydraulic consideration and design part 3. Thank you.